975 meters of steel, wider than a 6-lane highway, heavier than a fleet of locomotives stacked end to end, and it vanishes beneath the ice of the Arctic Ocean, without a ripple, without a sound carrying enough firepower to reshape the surface of the Earth 200 times over. Welcome back to the channel. What you are about to hear is the story of one of the most extreme, most audacious, most physically overwhelming feats of submarine engineering ever attempted by human hands. This is the Typhoon class, Project 941. The Russians call it Akula, the shark. NATO calls it Typhoon. The world calls it the largest submarine ever built. And that title is not a marketing claim. It is not a figure of speech. It is a measured, documented, verified, undisputed fact. No submarine before it reached this size. No submarine since has come close. No underwater vessel in the history of naval engineering, military or civilian, crewed or uncrewed, has ever matched what you are about to witness. This is not just a submarine. It is not merely a vessel that sinks below the waterline, creeps through the deep, and returns to port. This is an underwater fortress, a mobile, self-sustaining, nuclear-armed city encased in high-strength steel, capable of operating for months beneath polar ice, without resupply, without surfacing, without a single radio transmission, invisible to satellites, invisible to patrol aircraft. It is two complete submarines, two fully independent pressure hulls, arranged side by side within a single massive outer body, like two hearts beating inside one chest, and nestled between those two hearts standing upright in the darkness. 20 ballistic missiles, each one approximately 16 meters tall enough to stand beside, each one weighing around 84 tons, each one carrying 10 independently targeted nuclear warheads. That is 200 nuclear warheads on a single vessel beneath the Arctic ice. In silence, think about that for a moment. Let the scale settle in. Now imagine the challenge. You build a submarine large enough to carry the biggest ballistic missiles ever deployed at sea. The R-39, the largest submarine-launched ballistic missile any nation has ever put into service. Build it strong enough to dive to hundreds of meters below the surface, where the pressure of the ocean would crush ordinary steel like aluminum foil. Build it quiet enough to evade the most advanced hydrophone networks and sonar arrays on the planet. Build it to operate in the Arctic in water so cold that an unprotected human body would lose consciousness in minutes and die shortly after. Build it to surface through solid ice that can be over 2 meters thick. Build it to sustain a crew of approximately 160 men for months at a stretch. Without sunlight, without fresh air, without any physical connection to the world above. Build it to be home, barracks, power plant, weapons platform, and ghost simultaneously, without compromise, in a single hull. And they looked at all of that and said, "We'll do it." But not in a single hull. Before we continue, make sure you are subscribed to the channel and that you have hit the notification bell. We go deep, sometimes literally, into the world's most extreme engineering projects, and you will not want to miss what comes next. Stay with us until the very end of this one, because the way they solve the single most fundamental problem in this submarine's design is something that had never been attempted before in the history of naval architecture. Not by any nation, not for any vessel. It was a first, and it changed everything. Now, let us go back to the very beginning, before the steel, before the welding, before the first rivet and the first reactor. At first, there was only a strategic question, a question posed in the early 1970s, at the frozen peak of the Cold War, in the classified conference rooms of Soviet Naval Command. The question was deceptively simple and terrifyingly, how do you guarantee a second strike? How do you ensure that even after a devastating nuclear first strike against the Soviet Union, even after the land-based intercontinental missile silos are craters, even after the strategic bomber airfields are smoking ruins, even after the command bunkers are buried under megatons of explosive force? The answer, they decided, would not live on land. It would not fly through the air. It would live beneath the ocean, beneath the Arctic ice cap, In a submarine so large, so deep diving, so silent, so utterly invisible that no adversary, no matter how powerful, no matter how technologically advanced, could ever find it, track it, target it, or destroy it before it launched its full payload. But there was a problem, a very specific, very physical, very stubborn problem that no amount of strategic ambition could wish away. The missiles, the Soviet Union's defense industry had developed the R-39 designated SS-N-20 Sturgeon by NATO. It was a formidable weapon. It was also, by a significant margin, the largest submarine-launched ballistic missile ever deployed by any nation on Earth, approximately 16 meters from base to nose cone, roughly 84 tons of propellant, guidance systems, warheads, and structural casing. For context, the American Trident C-4 missile of the same era was shorter, narrower, and substantially lighter. The R-39 was a giant among giants, and the Soviet Navy did not want 5 of them on a submarine, or 10, they wanted 20. If you designed a conventional single-hull submarine to carry 20 of these missiles vertically, the hull diameter would need to be enormous. And here's the engineering trap. The larger the diameter of a pressure hull, the thicker the steel must be to withstand deep ocean pressure. The thicker the steel, the heavier the hull. The heavier the hull, the more ballast and buoyancy you need. The more buoyancy you need, the larger the outer hull must be. The larger the outer hull, the more drag, the more noise, the more power required to move it. Every increase in one dimension cascades through every other dimension. It is a spiral that, for a conventional design, leads to a submarine that is either too heavy to dive, too large to maneuver, too noisy to hide, or simply too complex to build. If you reduce the number of missiles, you weaken the strategic mission. If you redesign the missiles to be smaller, you would lose years of development, time billions in resources, and range and payload capacity. If you force the hull wider, the metallurgy became impossible. No shipyard could fabricate and weld pressure, hull plates of the thickness required. If you made the steel stronger, the weight became unmanageable. If you accepted shallower diving depths, you made the submarine more vulnerable to detection. Every orthodox approach hit a wall. So the solution was not orthodox. It was not a wider hull. It was not a modified version of an existing class. It was a concept so radical that many within the Soviet naval establishment initially doubted it could work. The team at the Rubin Central Design Bureau for Marine Engineering in Leningrad, led by chief designer in decorated submarine architects in Soviet history, proposed something that had no precedent. Instead of one pressure hull, build two complete, independent, cylindrical pressure hulls, each approximately 7 meters in internal diameter, arranged side by side like the twin barrels of a shotgun. Each hull would be a fully functional submarine in its own right, with its own compartments, its own systems, its own reactor and propulsion line. The Fen wrapped both of them together. Inside a single, massive outer hull, the light hull, the hydrodynamic casing that would give the entire assembly the smooth, streamlined shape of a submarine. And in the space between those two inner hulls, in the central cavity that runs along the forward section of the vessel, forward of the sail, that is where you place the missiles in 20 vertical launch tubes, standing in the gap between two submarines, inside a third. This was not a submarine. This was two submarines fused into one body and given a single mission. And now the construction began. The only shipyard in the Soviet Union with the physical capacity and the security clearance to build something of this Sibird-Biska, Ifrud, Vince sits on the southern shore of the White Sea. Deep inside the Russian Arctic, it is not a gentle place. It is not a forgiving place. Winters last 6 months or more. Temperatures fall to 30, 40 degrees below zero. The White Sea freezes solid. It comes off the Barents Sea, relentless, cutting, bone deep. This is where the largest submarine in history would be born. Not in a temperate port, not in a sheltered bay. In the Arctic, the scale of preparation was immense. Steve Mash had built submarines for decades, hundreds of them, including earlier classes of ballistic missile submarines. But nothing of this size, nothing of this width, nothing of this complexity. The construction halls had to be assessed, expanded, and in some cases fundamentally reconfigured to accommodate a vessel 175 meters long and 23 meters wide. New gantry cranes had to be installed. Cranes capable of lifting entire hull sections weighing dozens of tonne. New welding stations had to be built. New jigs and fixtures designed and fabricated to hold hull segments in precise alignment during assembly. New quality control laboratories equipped with X-ray machines, ultrasonic testing equipment, and magnetic particle inspection systems. In Go, the shipyard did not just build a submarine, it first had to rebuild itself. Then came the steel. Submarine pressure hulls are not made from ordinary structural steel. They are fabricated from specialized high-strength steel alloys engineered to withstand the crushing hydrostatic pressure of the deep ocean while remaining weldable, formable, and resistant to the corrosive effects. The properties required are extreme. High yield strength, high tensile strength, excellent fracture toughness at low temperatures, and a chemistry that allows consistent defect-free welding. The steel plates arrived at Severmash from specialized Soviet metallurgical plants, rolled to precise thicknesses, cut to precise dimensions, inspected for internal defects before a single weld was struck. Each pressure hull was constructed in sections: cylindrical rings, conical end caps, hemispherical bulkheads. Each section was formed from steel plate, rolled into curves, welded at seams, inspected, stress, relieved, and inspected again. The welding was the critical act. Every weld seam on a submarine pressure hull is a potential catastrophic failure point. At depth, the entire ocean is trying to crush the hull inward. The welds must be as strong as the parent metal, or stronger. The welders who performed this work were among the most highly trained and rigorously certified in the Soviet Union. Their procedures were exacting. Every weld pass was performed according to strict protocol: preheat temperatures, interpass temperatures, filler metal selection, shielding gas composition, travel speed, amperage. Nothing was left to judgment. Nothing was improvised. And after every weld was completed, it was subjected to a battery of non-destructive tests: radiographic inspection to find internal voids, ultrasonic inspection to detect subsurface cracks, magnetic particle inspection to reveal surface defects, dye-penetrant inspection to catch what the other methods might miss. Every seam mattered. Every millimeter mattered. A single defect, undetected, could mean the loss of the submarine and everyone aboard. The completed hull sections, each one a massive ring or cone of inspected, certified steel, were then transported within the shipyard to the main assembly hall. There, they were aligned using precision optical instruments and laser systems, brought together and welded into continuous cylinders, 2 of them, side by side, each one a complete pressure hull, divided internally into compartments by transverse bulkheads, thick steel walls that subdivided the hull into isolated sections. If one compartment flooded, the bulkheads would contain the water and preserve the buoyancy and structural integrity of the remaining sections. Redundancy, engineering philosophy of the entire Typhoon was built on these principles. Then came the outer hull, the light hull. This was the final layer, the skin that wrapped around both pressure hulls and gave the submarine its external shape. The outer hull was fabricated from lighter steel. It did not need to withstand deep ocean pressure. Only hydrodynamic forces and the structural loads of surface operations and ice surfacing maneuvers. It was shaped to minimize drag, reduce turbulence, and channel water smoothly over the submarine's enormous body. The result was the Typhoon's distinctive silhouette: broad, flat-topped, almost whale-like. Unlike the narrow, cigar-shaped profile of most submarines, the Typhoon was wide and imposing, 23 meters across. It looked less like a submarine and more like an underwater aircraft carrier. Between the 2 pressure hulls, in the forward section of the boat, the missile compartment took shape. 20 vertical launch tubes, fabricated from high-strength steel, structurally integrated with both pressure hulls and braced against the inner surface of the outer hull. Each tube was engineered to house a single R-39 missile in launch, ready conditioned for the duration of a patrol, which could last months. Each tube included its own gas generation system for cold launch ejection, watertight hatches at top and bottom, environmental monitoring, sensors, shock isolation mounts to protect the missile from hull vibrations. The atmosphere inside each tube was controlled temperature, humidity, chemical composition to preserve the missile's solid propellant, its guidance electronics, its warhead systems, 20 tubes, 20 missiles, 200 warheads, all standing silently in the darkness between two hulls, waiting. Then came the reactors, E2OK -650 pressurized water nuclear reactors, one installed in each pressure hull, each powering its own independent propulsion train. The OK-650 is a compact, highly enriched uranium reactor that generates approximately 190 megawatts of thermal energy. Energy heats pressurized water in the primary coolant loop, which transfers its heat to a secondary loop via steam generators. The secondary loop produces high-pressure steam, which drives the main turbines, which turn the reduction gears, which rotate the propeller shafts. 2 reactors, 2 turbine sets, 2 shafts, 2 propellers in full redundancy. If one entire propulsion line failed reactor, turbine shaft, and propeller, the other could still drive the submarine home. The reactor compartments were surrounded by layers of biological shielding lead, steel polyethylene, water to reduce radiation exposure to the crew. The shielding was massive. It added hundreds of tons to the submarine's displacement. But without it, the crew would not survive a patrol. The propellers themselves were a study in acoustic engineering. Noise is death for a submarine. In the deep ocean, sound propagates across extraordinary distances, hundreds of kilometers under the right conditions. A submarine that generates detectable noise is a submarine that can be found, tracked, and destroyed. The Typhoon's propellers were designed with blade geometries, impertided to minimize cavitation, the formation of microscopic vapor bubbles along the blade surfaces at high rotational speeds in the number of blades, the pitch, the skew, the rake, the tip, profile. Every parameter was calculated, tested, refined, and tested again. The shaft bearings were mounted on resilient mounts to isolate propeller vibrations from the hull structure. The reduction gears were machined to extreme tolerances to eliminate gear noise in every component in the propulsion chain. From reactor core to propeller tip was evaluated not just for power and reliability, but for silence. And then the outer hull received its final invisible layer of Armprowston, anechoic coating. Thousands upon thousands of individual rubber tiles, each one engineered to absorb incoming sonar pulses rather than reflecting them back to the searching vessel. The tiles worked on the principle of acoustic impedance matching and internal sound absorption, converting sonar energy into heat rather than bouncing it back as an echo. Each tile had to be bonded directly to the outer hull surface using specialized adhesives. Each bond had to be perfect, no air gaps, no loose edges, a single missing tile. A single detached section could create a reflective spot that sonar operators could detect. The tiling process was slow, meticulous, and performed largely by hand. Workers crawled across the hull surface, applying tiles one by one, checking adhesion, sealing edges. It was among the least glamorous and most critical steps in the entire construction process. Then came the interior outfitting, the work that turned a steel shell into a habitable vessel. Miles of electrical cabling, power cables, signal cables, fiber optic lines, coaxial cables for communications routed through both pressure hulls, through cable trays and conduits and penetrations in every bulkhead, and thousands of pipes. High-pressure hydraulic lines for the diving planes and rudder. Low-pressure cooling water lines for electronics. Steam lines from the reactors. Drainage lines, sanitary lines, fire main lines, compressed air lines at multiple pressure ratings. Hundreds of valves, gate valves, globe valves, ball valves, check valves, relief valves, remotely operated valves, in pumps for ballast water, pumps for reactor coolant, pumps for bilge drainage, pumps for freshwater generation, air conditioning units, air filtration systems with activated carbon scrubbers and electrostatic precipitators, oxygen generation systems using electrolysis to split purified water into breathable oxygen, in carbon dioxide removal systems using chemical absorbents, atmospheric monitoring systems that continuously sampled the air for trace contaminants, carbon monoxide, refrigerant leaks, hydrogen buildup, volatile, organic compounds, navigation systems, ring laser gyroscopes for inertial navigation, multiple sonar arrays included, the fire suppression systems in every compartment, halon and foam systems with thermal detectors and manual alarm stations, damage control lockers positioned throughout both hulls, stocked with shoring timbers, welding equipment, portable pumps, breathing apparatus, and patching materials. And then the features that made the Typhoon a legend beyond its weapons. A small plunge pool, a swimming pool aboard a submarine, something almost absurd in concept, yet profoundly practical in purpose. A sauna with wooden benches and electric heaters, offering the crew a brief sensation of warmth and normalcy in an environment defined by cold steel and recycled air. A lounge area with comfortable seating, a television, a film library. These were not indulgences. They were calculated investments in crew endurance. A strategic patrol beneath the Arctic ice could last 2 months, 3 months, longer. The crew would not see the sun. They would not feel the wind. They would eat the same food, breathe the same recycled air, hear the same mechanical hum, walk the same steel corridors, day after day after day, without outlets for physical activity and mental relaxation. Morale collapses, and on a submarine carrying 200 nuclear warheads, morale is not a luxury. Every detail of crew comfort mattered. Every hour of rest mattered. The lead boat, TK-208, was laid down at Submarine in 1976. 5 years of cutting, bending, welding, inspecting, installing, wiring, plumbing, testing, retesting, correcting, and certifying. In December 1981, TK-208 was commissioned into the Soviet Navy. 5 more hulls followed over the next 8 years. TK-202, TK-12, TK-13, TK-17, and TK-20. 6 Typhoons in total, each one built on the same staggering scale, each one carrying the same awesome payload. The last was commissioned in 1989. In the final months before the world the Typhoon was built to defend against began to change forever. Then came sea trials, the moment of truth. Every system tested under real-world conditions for the first time. Reactors brought to criticality, in propulsion engaged, the submarine taken to depth slowly, methodically, with every gauge watched, every sensor monitored, every hull sound analyzed, diving to approximately 380 to 400 meters. At that depth, the ocean exerts pressure of roughly 40 atmospheres on every square centimeter of hull surface. The hull flexes. It groans. It speaks in sounds that only submariners know. The deep, resonant creaking of steel under compression, the pop of fittings settling, the whisper of water finding its way along the outer skin. The crew listens, the instruments watch, and if everything holds, if every weld is sound, every seal is tight, every system performs, the submarine is certified for operational service. Speed trials followed, the Typhoon reaching approximately 25 to 27 knots submerged. That number sounds modest, beside a surface warship doing 30 knots. But remember, what is moving is approximately 48,000 tons of steel, machinery, weapons, and crew, displacing a volume of water equivalent to a small lake, accelerating through a medium 800 times denser than air. That is not speed. That is controlled defiance of physics. Every knot of velocity demanded thousands of horsepower. Every knot generated noise that had to be suppressed. Every knot tested the hull, the shafts, the seals, the bearings, and the courage of the crew. And then the Arctic. The mission the Typhoon was born for, navigating beneath the polar ice cap, thousands of kilometers of frozen ceiling overhead. No surface access, No emergency surfacing possible except in the rare Polonius, natural gaps in the ice, inferdentious. The submarine sail was reinforced with hardened steel for exactly this purpose. Surfacing through Arctic ice is not a gentle process. The submarine rises slowly, pressing the top of the sail against the underside of the ice, then increasing buoyancy until the ice cracks, splits, and shatters upward in an explosive spray of frozen fragments. The sound is violent, a deep, grinding roar as millions of tons of ice resist and then yield. And then the Typhoon sits in the broken ice, its missile hatches exposed to the freezing Arctic sky. 20R negative, 39 missiles, 200 warheads, ready. Most people who have ever seen a photograph of the Typhoon see only a shape, a dark silhouette in gray water, a wide, flat hull with a distant sail rising from its center. They see a machine. They see a weapon. They do not see the two pressure hulls hidden inside that shape, running side by side, separated by meters of empty space, each one a sealed world of its own. They do not see the 20 missile tubes standing in the darkness between those hulls, each one a column of precision engineering, holding a weapon capable of striking a target thousands of kilometers away. They do not see the thousands of anechoic tiles bonded to the outer skin, each one placed and pressed and sealed by hand in freezing shipyard conditions. They do not see the two nuclear reactors buried deep within the hull, each one producing enough thermal energy to power a small city, wrapped in hundreds of tons of radiation shielding. They do not see the miles of cable, the thousands of pipes, the hundreds of valves, the dozens of pumps, the filtrogen generators, the carbon dioxide scrubbers that keep the air breathable and the water drinkable. They do not see the welders who spent years perfecting every seam, every joint, every penetration in the pressure hull, knowing that their work would be tested not by inspectors alone, but by the full weight of the Arctic Ocean pressing inward at 400 meters of depth. They do not see the crew. Approximately 160 men living inside two steel cylinders beneath the ice, carrying the burden of a strategic mission so consequential that its mere existence reshaped the geopolitics of the planet. The Cold War ended, the Soviet Union dissolved, and one by one, the Typhoons fell silent. Most were decommissioned during the 1990s, and several were dismantled with financial assistance from the United States through the Cooperative Threat Reduction Program, a strange and remarkable irony in which the nation these submarines were designed to annihilate helped pay for their peaceful dismantlement. The R-39 missiles were withdrawn from service. The reactors were defueled. The hulls were cut. The last active Typhoon. TK-208, renamed Dmitry Donskoy, served for years not as a weapon of war, but as a test platform for the RSM-56 Bulava, a new generation submarine launched ballistic missile. Even in retirement, the Typhoon served, but the legacy is not in the metal. Metal can be cut, melted, reformed. Metal forgets. The legacy is in what the metal represented. The idea that human beings working in Arctic shipyards, in freezing darkness, with steel plate and welding torches and engineering calculations, and sheer unyielding determination, could conceive of a Procton's 5 meters long, 23 meters wide, displacing approximately 48,000 tons beneath the waves, containing 2 complete pressure hulls. This was not engineering. This was an act of collective will, made physical in steel. This was not construction. This was the answer to an impossible question, a question asked in fear and answered in precision. This was the Typhoon, Project 941, Akula, the largest submarine ever built, and for a generation, the most powerful weapon on Earth, not because of the destruction it could unleash, but because of the silence in which it waited. If this story moved you, or amazed you, or simply made you see the world a little differently, subscribe to the channel, hit the notification bell, leave a comment below, telling us what engineering mega project you want us to explore next. We read every one. Thank you for watching. We will see you in the next one.